All right, good afternoon. Today is Thursday, November 19th, and we are going to finish up our discussion of descriptive statistics, and then we're going to start our discussion of inferential statistics. Before we get started, are there any administrative questions? Did we get the grades on the midterm corrected? Okay. All right. Yes. When's the third midterm? The third midterm's on the last day of instruction. I believe that's not next Thursday, because next Thursday you're going to be at home. But then the week after, I believe it's that week, that Thursday. December 3rd. All right. We were talking about standardizing scores. Let me remind you what we were saying. We were saying that in social sciences, we make up scores all the time, more than probably any other science. We make up scores. We make up, this is your personality score. This is your IQ. This is your locus of control. And these are pretty arbitrary scales. And so knowing that you've got a 17 on a score or on a scale doesn't give you all of the information that you need in order to understand where you fall compared to everyone else. Yes, you got that rationale to begin with? So what we can do is we can create standardized scores. And we use what we know about the mean and the standard deviation, because we just learned that when we say something is normally distributed, that is giving you very specific information about the relationship between the mean and the standard deviation. So we use the mean and the standard deviation to create these standardized scores. So we said, here is one scale that has a mean of 18 and a standard deviation of 4. Here is another scale that has a mean of 25 and a standard deviation of 3. We sketched out what do those descriptive statistics look like, what are those distributions. And then we said, let's jump up and down the scale in units of the standard deviation. So we jumped the mean plus 1 standard deviation, the mean plus 2 standard deviations, the mean plus 3 standard deviations. Yes? Remembering all of this? It's all coming back? And we did the mean minus 1 and the mean minus 2 and the mean minus 3. And we laid it all out so that we could draw our distributions. We then said, let's write that as a standard equation. The score equals the mean plus, and I pulled this letter Z, apparently out of thin air. I didn't actually pull it out of thin air. It is actually a statistic. But so the score is the mean plus Z standard deviations. And then we were doing a bunch of algebra, weren't we? If we've got the score equals the mean plus Z standard deviations, let's solve for Z instead. First step would be to subtract the mean from both sides. The next step would be to divide by the standard deviation. So you'd end up with Z equals the score minus the mean divided by the standard deviation. So if you know that you have a Z of 3, what does that mean? Are you above the mean or below the mean? Are you a little bit above the mean or a whole lot above the mean? A whole lot. How many people or how much of the percentage are higher than you? Oh, that was that other sheet of paper. Like 0.5%. Do you remember? I'm actually going to make you remember these things and put them all together. Right? So this was the mean plus 1, plus 2, plus 3 standard deviations. It's all normal distributions. We're assuming that it's all the same. So if you've got a Z of negative 1, are you above the mean or below the mean? Are you a whole lot below the mean or a little bit below the mean? a little bit below the mean. So on homework 8, you have a whole series of working with z-scores. So I will try to release that today or tomorrow so that you can get started on it while it's still fresh in your mind. I highly recommend that you sketch it out like that. I also highly recommend that you say, let's see, for the red distribution, this is a z of 1, this is a z of negative 1, this is a z of 2, this is a z of negative 2, this is a z of 3 and negative 3. And that for the blue distribution, where were we? Mean of 25. So this is 1, 2, 3, negative 1, negative 2, negative 3. It's hard to see where I put those. But just so you could just put them out there like that, and there you've got some z's to calculate, to check back on. Let me put you to the test. With your clickers out, feel free to work with your neighbors on this question. This is an easy one. Easy, easy, easy. Oh, might help if I turn that on, huh? Have you got it? So is a z-score of 1, is that going to be higher than the mean or lower than the mean? Okay, so which ones can you eliminate? A and B. All right. How much higher than the mean is a z-score of 1? 325. Yes? Are you all there now? Oh my goodness, you've all got it right. This is a tough one. You're going to have to figure out what is the z-score for each of those, and then say, compare the z-scores. Which z-score is bigger? Do you want the equation for z again? We said z equals the score minus the mean divided by the standard deviation. Okay, you ready for the numbers again? So what is relatively better? Which one of those has a higher z-score? All right, I'm seeing a bunch of you there. How do you figure out what the z-score is for 1030 on the SAT? What's the equation? It's 1030 minus 1518 divided by 325. Hang on, I'm just going to pop back to here. So that's the equation. Someone who's got a calculator out, what's 1030 minus 1518? Negative? Oh, the whole score is negative 1.5? So you get a z of negative 1.5? Yes? And then is that the equation for 14 on the ACT? So it's 14 minus the mean divided by the standard deviation, negative 1.4. Okay, so which one's better? Which one's less bad? Okay, I've got about 85% of you answering correctly. You seeing what you're doing? Yep, all right. Uh-huh. Yep, negative 1.5 is further below the mean than negative 1.4 because it's you know how far down that curve is it going, and so you just then can look at those and say these are now standardized and they are I can directly compare them. I can't directly compare 1030 and 14. I can't directly compare that. I can't look at that and say, oh, this one's better than that one. I need to standardize them in order to be able to compare them because they're then all on just a standard scale. So a few key points about standard scales. We calculate them because we're interested in these constructs that can't be directly measured. So we make things up and they're arbitrary. We make them up really cleverly, but they are arbitrary. They're not tied to anything physical. And so using what we know about that normal distribution, we can standardize the scores. Therefore, we can compare them. So the z-scores allow us to make that comparison. All right. Let's take another look at, we're just going to go back through some of the examples that we've been using across the quarter and look at their descriptive statistics. All right. So you remember this example, when less is more, the bronze medalists and the silver medalists and the agony to ecstasy scale. And we explained this, we thought about this earlier in the quarter, and this is the results that they presented us. What is being graphed here? What does that line represent? Okay, so is the immediate silver, and is it a particular person's score? Is it a z-score? Is it what is it? It's an average. It's the group average of the people who, right away, those that won silver, this is their average agony to ecstasy scale. This is their average. The bronze winners immediately, as soon as they knew, this is their average. Looking at this information, do you predict that there is a main effect of silver versus bronze? So you can look at that and you can kind of average this bar and that bar together, and this bar and that bar together, and just make a guess, an educated guess. Do you think there's going to be a main effect of medal type? Yes, in what direction? Bronze is happier. Yes? Doing the same thing. Looking at immediate, main effect of immediate, average those together. So kind of squint and think the average of those would be about here. And average those together and squint and think the average would be about here. Does it look like that? Do you suspect that there'd be a main effect of time? That right away and then by the time you get to the medal podium? And how might you, which one's higher? Which ones, what are they doing? By the time they get to the medal stand, they seem to have calmed, everyone seems to have calmed down some. Looking at the interaction, if you were to draw a line from there to there, and draw a line from there to there, do they look roughly parallel? Does the difference here look roughly the same as the difference there? Yeah. So we're probably not expecting an interaction. They all calm down regardless of the medal type. So over the time, they all calm down regardless of the medal type. That's what you're predicting, right? Let's see what they said. When assessing the athlete's immediate reactions, participants assigned the bronze medalists a mean happiness rating of 7.1, 7.2, but the silver medalists a mean rating of only 4.8. So they're using that word only to make the comparison. This group is happier than that group. They're reporting their means and standard deviations. We're going to be practicing this, right? And look how cleverly they have talked about their operational definition. They didn't actually run down and measure their happiness. They didn't have a thermometer jabbed into the athletes' foreheads. It was the participants assigned the medalists happiness ratings. Do you see how they've got their operational definition even there in that one sentence about the results? And then, so that's the first main effect. Here's the second main effect. When they're examining the athletes on the medal stand, they assign the bronze medalists a mean rating. Oh, so no, this is just both of the, both levels of medalists at both occasions. These data were analyzed with a 2 type of medal, bronze versus silver, by 2 tape, immediate versus medal stand, analysis of variance, ANOVA. Don't worry about it. We're going to talk about it next week. This analysis revealed two significant main effects, but no interaction. You guys understood that, didn't you? You predicted it, and you understood it. So it's a 2 by 2 factorial design. Both 2 significant main effects, but no interaction. And then they go on and they say the main effect of tape. This is the statistic and why they can say that. Look, P less than 0.05, we knew to look for that. The main effect of tape, oh, this is kind of annoying. So they've said, they've called one of their variables, they would not have passed this class. They've called one of their variables tape. Immediate versus medal stand. I'm surprised they got through the editor. Because, I mean, you can kind of see that, I mean, it was back in the 90s and the 2000s, they had actual physical videotapes. And so what tape is that on? It's on the medals, you know. Time would have been a much more, you know, I don't know, tape is a really lousy variable label. The TAs would have had something to say to them, wouldn't they? So, and then look how awkward it becomes when they continue to discuss it. Because you're like, well, what does tape mean? The main effect of tape indicates that the athletes on the whole looked happier immediately after their performances than when they were on the medal stand. More importantly, the main effect of type of medal indicates that the athletes who finished third looked significantly happier than those who finished second. And that was exactly what you read from that graph. Let's look at another one. So this is the self-esteem and love, this is the sit back to back with your sweetie pie and fill out the questionnaires and name things that you dislike about your partner. All right. So again, we've got 4 different groups, and this time it's 4 completely different groups, whereas last time it was 2 groups at 2 different times. So we've got the control group and the experimental group that walked through the door with high self-esteem and that walked through the door with low self-esteem. So let's ask the same question. Do you think if we average the high self-esteem and we average the low self-esteem, do you think there might be a main effect of self-esteem? Yes. And the simplest way you would say that would be people with low self-esteem rate their partner worse or less attractive than people with high self-esteem. And if you looked at the control and the experimental, do you think that there's a main effect? And you think it would say something like, those in the control condition, or those who had thought that they were being rejected, rated their partner as less attractive than those who had not just experienced rejection. So then drawing a line from there to there, and drawing a line from there to there, do those lines look parallel? Is this difference the same as this difference? Nowhere near, right? Do you suspect that there's an interaction? Yes. Let's see what they said. So our analysis revealed a significant main effect for condition, and that's how they get to say it. A significant main effect for self-esteem, that's how they get to say it. And a significant condition by self-esteem interaction. Again, you guys nailed it. Yeah? Yes. I'm expecting you to just look at it right now and take a deep breath and say P less than 0.05, that's what we know. You're going to know so much more about T by the time you leave today. And Thanksgiving, it's going to be all you can talk about. Because you'll have today's lecture and Tuesday's lecture, and it will be like, oh my God, I learned the coolest thing this week. Okay? Do you see how formulaic and similar these results sections sound? They were written decades apart, but that we've got this very formulaic way of presenting our results. All right. I think we have come to the end of the descriptive statistics portion of the class. What do you guys think? Any last questions about the descriptive stats, or are you ready for the end of section quiz? They're ready. All right? Here we go. Oh. There we go. Okay. All right, and I'm seeing most of you there. Go ahead and put in your best answer. And I'm going to move on. The typical value is the central tendency. All right, and I'm seeing most of you there. And tightly clustered means that it would have a small standard deviation. All right, and I'm seeing most of you there. So a continuous variable that is not skewed, that would mean it's symmetric, that would mean it's normally distributed, that means that we would be calculating the mean. If it is skewed, we'd be calculating the median. Can you see the red and the blue? Yes, okay. All right, and I'm seeing most of you there. And the red and the blue are right there, right at the same space, so they're at the same central tendency, the same mean, but they have different spread, different variability, different standard deviation. All right. Moving right along. Let's get some of those inferential statistics concepts out. So we're going to talk about the purpose of inferential statistics. We're going to talk about hypothesis testing. We're looking for differences that are not due to chance. We're going to take random effects or chance into account. We're going to look at decision making, and we're going to describe two different types of errors that we can make, and we're going to talk a little bit about power and effect size. Are you ready? So first off, just put your pencils down and just listen for a minute. I've got a really inane example. We want to see if there is a statistically significant difference in age between first and second grade students. We're going to walk down to our local elementary school, and we're going to ask 5 first graders and 5 second graders how old they are. Here is our data. This is one sample of first and second grade students. What would we do first? So we're going to want to describe them, right? We're going to want to add those up and calculate the means. So we're going to start with describing the data. It's continuous. We will assume it's normally distributed. So we've got a mean of 6.04 and a standard deviation of 0.598. And then for the second sample, we've got a mean of 7 and a standard deviation of 0.432. So we're kind of asking the question, are these two samples from the same population, or are these two samples from different populations? Because we know every time we draw a sample, there's going to be some variation. It's going to be a little bit different. You remember the beads and the paddle, and every time we draw a sample, it'll be a little bit different. Are these two samples different enough for us to say they come from different buckets? So let's see, what do those describe? So here are the first grade students, and we know normally distributed is secret code, and it means that there is this very specific relationship between the mean and the standard deviation. So there we have the mean and the standard deviation. That's the distribution of first grade students. If I came back, do you see these dots? If I said, I've just drawn another sample of 6 students, is that likely to be from first grade students? What do you think? Yes or no? It's a yes or no question. Mumble, maybe. Yeah, I say yes. They're all under that curve, right? Yeah? But if it was from that same population, what proportion should be between plus and minus 1 standard deviation? 68% of them. Have we got 68% of them in there? Oh, no, we really don't, do we? We've got like half that. We've got 33% in there. So we'd say, I don't think that that's likely from this distribution at all, from this population at all. I think it's likely from a different population. How about if I said, I just went down and got another sample of 6 students. Does this look like it's likely drawn from the same population? Yes. So we are going to be drawing samples, and we don't know if the populations are the same or different. And we're going to be making a decision about whether we think the populations are the same or different, based on what we know about the mean and standard deviation and normally distributed variables. So here are the two samples that we have drawn, and we're asking, so these are the sample distributions. I wonder if they both come from the same underlying population distribution. So we could look at this and go, okay, so the mean of first grade students, wow, is right here in the tail of the second grade students. It's pretty rare to get an observation out here, isn't it? It would be highly unlikely that a sample that was drawn from this distribution had a mean all the way down here. I mean, it could happen just by random chance, maybe, but we want to know, what's the chance of that happening? If the probability of that happening is really small, then we're going to feel pretty confident saying they're not drawn from the same population. So if I said that's a sample, is that likely to be first grade students or second grade students? And it couldn't be second grade students, could it? Based on that, on what we know about the sample of second grade students. All right. So that's kind of just a graphic or visual way of thinking about it. Let's put some words to it. So inferential statistics give us an objective measure of the probability that any observed difference is due to chance. We know we're going to see differences because every sample is going to be different. What's the probability that that is due to chance? What's the probability that that is due to a real difference? These are called inferential statistics because they allow us to make inferences from sample back to the population. And remember, that population is that larger group that you're interested in. So you do that by taking into account the random error. We know that there's going to be sampling error, there's going to be noise. No two samples will be identical. And that's why we calculate inferential statistics. They allow us to make a decision. So they allow us to answer the question, did the treatment have an effect? Does the predictor variable predict a difference in the outcome variable? Does the independent variable cause a difference in the dependent variable? Or is the difference in the results just due to chance? That's what it's going to allow us to answer. Another way of saying that is, are the two samples from the same population, or are they from different populations? So let's take a look at hypothesis testing. We've got these two samples. We're asking, are there really two populations of students? You know, or is it really just one and that we've just taken two samples from that same population? So we're going to test hypotheses. We've been talking about hypotheses all quarter. Here is our research hypothesis. And I've told you before that you're going to hear it also called an experimental hypothesis or a working hypothesis or an alternate hypothesis. In this class, we're really trying to use research hypothesis because it seems to be clearest. We've been talking about the null hypothesis all term. So the null hypothesis always says the treatment doesn't have an effect. The independent variable does not cause a difference. The mean of one group is the same as the mean of the other group. So we could write the null hypothesis not in words as we've been doing, but in mathematical symbols and say the mean of group 1 is equal to the mean of group 2. That would be our null hypothesis. And it turns out that it's the null hypothesis that we can directly test. We can directly test, does the mean of group 1 equal the mean of group 2? And we will then draw conclusions about our research hypothesis. We've also been talking about directional and non-directional research hypotheses all quarter. Yes, so non-directional we've called two-sided. They specify that there'll be a difference without specifying which direction. And so if our null hypothesis was the mean of group 1 equals the mean of group 2, oh, I've lost my little mean, little bars. This research hypothesis would be the mean of group 1 does not equal the mean of group 2. A one-sided hypothesis needs to specify either the mean of group 1 is greater than the mean of group 2 or the mean of group 1 is less than the mean of group 2. All right, so we're going to test our null hypothesis. The fate of our research hypothesis depends on whether we can reject or fail to reject the null hypothesis. We talked a little bit about that last week where, boy, reject and fail to reject, the opposite of reject sounds like it should be accept. And it sounds very awkward to say fail to reject. But we never really want to embrace our null hypothesis. We're looking for a difference between groups. We can say we found a difference, or we can say we didn't find any evidence that there is a difference. But that doesn't mean I'm going to say that there's not a difference. We can't draw a strong conclusion. These are exactly the same. We're not able to do that. We can just say they're different, or I didn't find evidence that they're different this time, but I'll probably keep looking. So we're not directly testing the research hypothesis. We test the null hypothesis, and we either fail to reject it, which makes us kind of sad because we're looking for a difference. And if we don't find a difference, we can't draw a strong conclusion, and we're not sure what that means. Or we reject it, and in this case, rejection is awesome. Yes? So, if you want to prove that these are the same, that's a really difficult thing. You can prove that they're different. So, think about if I have a coin and I say this coin is weighted so that it will only ever flip heads. Okay? So I'm flipping heads, 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 okay? It just takes one tail till you go, oh, that hypothesis was not true. I've got evidence to support it, I've got evidence to support it, I've got evidence to support it. Oh, but it's only going to take one flip the other way to disprove it. The opposite, where I say, this is a fair coin, or no, this is not a, this coin will only flip heads, and it's flipping heads and tails. You're immediately saying it's flipping both heads and tails. So it has to. It's a common issue within all decision making, and we'll talk about decision making in some other realms as well. We also make decisions in the criminal justice. Well, how do we phrase it? So if you're accused of something and you go to trial and the judge bangs the gavel down, what is said? What is the phrase? Well, it isn't innocent until proven guilty, but then you have been found guilty, or you have been found not guilty. We can't prove that you didn't do it. We can prove you did it. We can say we don't have enough evidence to show that you did it, but we can't prove that you didn't do it. So it's that same idea where we're going to be testing these are the same, and we're either going to say, no, they're not, and reject the null hypothesis, or we're going to say, we fail to reject, it's unclear how we're going to interpret that. So we've been talking about this example of does proximity predict action, where you were either very close to the one person you had to kill in order to save the 5, or you were very far away from the one person you had to kill in order to save 5. Yes? And so our hypothesis, our research hypothesis was closer proximity to the one person will make us less likely to save the 5. Our null hypothesis, proximity is not related to the likelihood of saving the 5. The difference in likelihood of saving the 5 is due to chance alone. That's another way of stating that null hypothesis. Oh my goodness, I got it 3 ways. The different proximity groups are from the same population with regard to the likelihood of saving 5. So the null hypothesis is saying, I split you guys into 2 groups, but I'm really just drawing from the same population when I asked that question. Okay. The answer is, I don't have enough information to decide. Are you ready? Do these look different? The answer is, I don't have enough information to decide. Do these look different? Oh, you don't have enough information to decide? Well, what other information would you need? You'd need the standard deviation. You'd need to know how spread out these scores were. So if I say, here is the distribution of one of those, do these now look pretty different? That's pretty far out there. If I said this was the distribution, you'll be like, oh, those are definitely from the same distribution. Those could easily be 2 samples from the same distribution. So we're going to be talking about whether or not we're going to be able to reject our null hypothesis. That is the goal. And so if these were our 2 samples, even before we get into the fancy inferential statistics, we could use the 2 eyeball inferential statistic and look at those and say, wow, getting a mean that is outside of the distribution of the other variable would be, or the sample, would make it highly unlikely that those are 2 samples from the same population. So that's where we're going. First off, let's talk about decision making. I want you to imagine for a moment that you have scientist superhero X-ray goggles. And when you put your scientist superhero X-ray goggles on, you can see the true state of the world. So in the true state of the world, the null hypothesis is either true or it is false. If the null hypothesis is true, does that mean that there is a difference or there isn't a difference? No difference. So there's either no difference or there is a real difference. But we don't have those superhero scientist X-ray vision goggles. So we're left making a conclusion. The projector turns off after 2 hours. We're left making a conclusion where we can either reject the null hypothesis or fail to reject the null hypothesis. Now, just thinking about it, sometimes you're going to make the correct decision. Anytime you make a decision in anything, sometimes it's going to be a correct decision. Sometimes it's going to be a mistake. It's going to be an error. And so we're going to go through and name the 2 different correct decisions that you can make and the 2 different errors that you can make. So if the null hypothesis is indeed true, there is no difference in the world, the correct decision would be to failed to reject the null hypothesis. So that would be correct, but it's kind of too bad. There was no difference, and you said that you didn't find a difference, but you were probably looking for a difference, so it's a little bit sad. But it's correct, and we can call that a true negative. I absolutely recognize that in this section of the class, we're going to be doing a lot of mental gymnastics of reject, that there's no difference, true, negative, that you need to be jumping back and forth and sort of negating and reversing a lot of words. Respect that, recognize that, give yourself time and practice to work that out. So, I think we're nearly back. There we go. So, if the null hypothesis is true and you fail to reject it, that's a correct decision, but we could call that a true negative. If the null hypothesis is actually false, there really is a real difference in the world, and you fail to reject the null hypothesis, you have made what we call a type 2 error, where there's a difference out there, but you couldn't find it. You missed it. Oh, and you see how I've done that this is, the world is white and the world is black, and your decision is white and your decision is black. And so the correct would be where the white match and the black match, and the incorrect would be the gray boxes where you're saying that the world is white and the world is actually black, or you're saying the world is actually black and the world is actually white. So how about when you reject the null hypothesis? You reject the null hypothesis, you say, when you reject the null hypothesis, what are you concluding? There's a real difference in the world. Oh! That could result in what we call a type 1 error, where you're celebrating, you popped the champagne, you found a difference, but if you had those X-ray superhero scientific goggles, you would know that there wasn't really a difference in the world. You could also call that a false alarm. And then finally, your decision is to reject the null hypothesis. In the real world, the null hypothesis really is false. You did it. That's a correct decision. It's a hit or a true positive. There is a difference, and you found it. Let's talk a little bit more about. We were just mentioning another place where we make decisions is in the criminal justice system. Let's talk a little bit more about that. So, there is a true state of the world. The null hypothesis is true, he is actually innocent, or the null hypothesis is false, he is actually guilty. But we don't know which of those is the case, right? We need to decide, we need to make a decision. So our conclusion, our judgment, is either going to be he's not guilty, or is going to be that he is guilty. So let's see where we end up. We conclude not guilty. He was really, so if we conclude not guilty, then the guy's going to go free, right? Regardless of the true state. Yes? So in this case, Is that a good decision? Yeah, that's a great decision. And in this case, we let a guilty guy go free. And that is the equivalent of a type 2 error. What happens if we conclude that he's guilty? Right? We're sending him straight to the gallows. Which one's the correct decision? So we concluded guilty. He was actually guilty. So that was the correct decision. And in this case, yikes. We just hung an innocent man. That sucks. We don't like doing that. To an extent, we could change our criteria. So, in our culture, do we tend to be more on, we're going to conclude that they're guilty on just a little bit of evidence because we'd rather not let a guilty man go free? That doesn't sound like us, right? Or do we say we're going to make the criteria for concluding guilty very strict and try to squeeze these errors? And the more people that we say, okay, we're going to conclude not guilty, we'll increase type 2 errors somewhat in squeezing type 1 errors. To a degree, those are related. It's not only related to each other. But you can imagine, you could say, I'm just going to say everyone's guilty. I'm never going to let an innocent, I'm never going to let a guilty person go free because I'm just going to conclude everyone's guilty. There you go. You've eliminated type 2 errors. Or you could just say, everybody's innocent. Everybody's not guilty. Everybody's not guilty. And in that case, you'll eliminate type 1 errors. But neither of those is a great solution. But to some degree, we can decide how strictly we're going to evaluate the evidence, and which of these we want to minimize. So let's go back and talk about those a little bit more. So type 1 errors are made when you've rejected the null hypothesis, but it was actually true. So another way of saying that, you have concluded statistically significant difference, but you got that by chance. The samples were really from the same population. We could call this a false positive. So whenever you have rejected the null hypothesis, you've got a chance of making a type 1 error or a chance of getting that hit. We don't want to make type 1 errors. We don't want to hang innocent people. So we want to set the probability of making a type 1 error very, very low. We want to set the probability of making a type 1 error at less than 0.05. Hey, you guys knew that already, right? So this is saying the probability of making a type 1 error is less than 0.05. We also will call this probability the alpha level, but not much. And what it means is there's a 5% chance that you think you're seeing a real difference in the world when none actually exists. I can live with that. Every time I make a decision, I might make a correct decision, I might make an incorrect decision. I want to make sure that my decisions are pretty good, but I can't be unrealistic. I can't always make a correct decision. Every time I make a decision, there's a chance I'm going to make an incorrect decision. And I can live with 5% chance that I'm seeing a real difference when none actually exists in the world. This is part of the reason why replication is so important in science, that I find a difference, but 5% of the time it's going to be just due to chance. And so if we can find it reliably, then we become more confident in it. If we can't replicate it, then we begin to think, well, maybe it's not out there, maybe it's not out there. So this is our decision rule for rejecting our null hypothesis. If the probability of making a type 1 error is less than 0.05, that's where we're going to reject the null hypothesis. Type 2 errors are when the null hypothesis is not rejected, but the research hypothesis is actually true in the real world. Here are some factors related to making a type 2 error. One of them is where you've set alpha. One of them is where you've set your significance level, as we said. Another thing that affects whether you're going to make a type 2 error is just your sample size. A small sample is not going to be as representative as a larger sample. There's going to be more variability. There's going to be more noise or error. The magnitude of the effect, or the effect size, is also going to influence your chance of making a type 2 error. So some things have a huge effect on our behavior, and some things have a tiny effect on our behavior. Do you remember way back when we were talking about the Stroop task, and we did like a pie of, that what you ate for lunch has a little bit, has a real effect, but it's just little. And so those are harder to detect than, say, your reading ability, which might have a huge effect. And so the magnitude of the effect, or the effect size, is going to affect our chances of making a type 2 error. We call this a false negative. Whenever you fail to reject your null hypothesis, you have a chance of making a type 2 error. You have a chance of making that miss. Yep, okay. Oh, this one. So, we set our alpha level. And so in science, we've set the alpha level at 0.05. And that's pretty consistent across science. And it's kind of gone down. A few decades ago, it was more like 0.1. But I think that now we're calculating so many more statistics that it might need to continue to go down, because it's so easy to calculate these statistics, and those probabilities add up. If I make one conclusion, I've got a 5% chance of making a wrong decision. If I make two conclusions, what's the chance that one of those was wrong? 10%. So they accumulate. This was an example from NASA where they were saying, we can't have something fail when it's on Mars. If we get a box of screws and there's one defective screw in that box, we throw away the whole box. We would rather throw away a good product than risk having a bad product, because we're sending the rover to Mars. Do you hear how what error they're willing to make and how they're changing their significance level? Whereas, if you got home and had a box of light bulbs and put one light bulb in and it was defunct, you wouldn't throw away the rest of the box, right? The risk of losing good things is more than the cost of finding out that something might be bad. So different industries, different situations would have, can balance these errors differently. Because they are somewhat related. Increasing the sample size reduces the risk of making either error. This is an example from your textbook about effect size. So you're camping and it's dark. You need to find something in your tent. You have a candle, and you're looking for your pet elephant. And you walk into your tent. Are you going to be able to find her? Yeah, because she's got a huge effect size. It doesn't take much power, much light to find her. You walk into your tent with a candle, and you're looking for an earring. Are you going to find it? Maybe, probably not. When you walk out of the tent, are you going to say, my earring is not in that tent? Or are you going to say, I couldn't find it? Do you hear the difference? You still don't know where it is. You could be in the tent, but you can't find it. You then come back with like a searchlight. Are you going to be able to find your pet elephant? Yes, she's still standing right there. Are you going to be able to find your earring? More likely, far more likely. And in fact, you can think about, there is a point at which, if my earring was here, I would be able to find it with this light. Do you hear what I'm saying? If it was here, I would be able to find it. And therefore, if you still can't find it, you're like, okay, I don't think it's here. And so this is all of these decisions that we're making, and this is the idea of power and effect size. So let's just talk about those. So power is that whether you've got a candle or whether you've got a searchlight. So it's the probability that a test will correctly reject a false null hypothesis. Oh my goodness, did you hear how many times you had to turn around in that sentence? The probability that a test will correctly reject a false null hypothesis. Let's go backwards. A false null hypothesis means that in the real world there is... So a false null hypothesis means that there's a null hypothesis, no difference. False null hypothesis, there's a real difference. Correctly reject, you said that there was a real difference. Do you get it? Oh my goodness, isn't it fun? And you seriously just have to keep turning around. Yep, so null hypothesis means there's no difference. A false null hypothesis would be there actually is a difference. Because the null hypothesis is false. And so you've correctly rejected it. So you have concluded that there is a difference and there actually is a difference. So this is the probability of finding a difference that does exist. Okay? Did you get there? The finding a difference that does exist? It's the power is related to our probability of making type 2 errors. And we can use it to reverse engineer that how much power would I need in order to know that I would be able to find it if it was here. So we can reverse engineer and calculate the sample size that would be needed to see if there was a real difference. Okay, you still doing okay? You still like me? You didn't like me to begin with. Never mind. So think about power as the size of the candle. Do you have a candle or do you have a searchlight? And it's very related to sample size. Oh, factors affecting statistical power. Increased sample size, it means an increased power. The magnitude of the effect, it relates to the statistical power. A smaller effect demands more power to detect it. You're going to need to have more power in order to find that earring. The type 1 error rate, the alpha level, the less risk you're willing to take, the more power you're going to need. Also, whether it's a between groups or a within groups design. Let's see if we can work that one out. Do you remember what was a between groups and a within groups design? So one of them is two different groups that you're comparing. The other is the same group of people doing two different tasks. Right? Which one of those is going to have lower variability? The within groups, because you're actually the same as yourself. And so that's going to reduce the variability. And so they, by definition, have more power that you would be able to detect an effect. So that's statistical power, and that goes together with this effect size. So that's how big's the effect, the magnitude of the effect. Does this, when we said, is it real, and then how big is it? When we talked about like the what contributed to your behavior on the Stroop test. When we look at effect sizes, we can say that there are small effects and medium effects and large effects. And here they are for our correlation coefficients. And I think we've looked at this before, maybe, where we say, if we get a correlation coefficient around 0.15, it's real, but it's tiny. If we get a correlation around 0.3, it's real, and actually in the social sciences, that's pretty huge. We get really excited about that. And a correlation about 0.4, or above 0.4, it means that it's a very large effect. And again, a smaller effect size requires larger samples in order to accurately detect. So when you make your decision, you state your decision in terms of the null hypothesis, where you're either going to reject or fail to reject. You then give your decision rule, your level of significance, your alpha level, the P, and so our decision rule is going to be, if P is less than 0.05, we reject the null hypothesis. If P is greater than or equal to 0.05, we fail to reject the null hypothesis. Let's just check that this is sinking in. Hang on one second. How about now? Okay. All right. I'm seeing most of you there. When we reject the null hypothesis, 90% of you are agreeing that means that we think that there is a real difference, that the difference is real. How about when we reject the null hypothesis? Oh, which row is that on? If we reject the null hypothesis, we're saying we think that it's a real difference. I think the true negative was there's no difference and I didn't find it. So it can't be the true negatives. It's got to either be a hit or one of those. Do you remember? Look it up. Do I trust you? 76% of you are agreeing. That it is the hit or the type 1 error. Stop it. All right. Where do I find a p-value? Where does this magical p-value come from? Why, you find a p-value by calculating an inferential statistic, of course. So when we are calculating an inferential statistic, here are the steps we take. We start by calculating our descriptive statistics. We then calculate the inferential statistic. We then look up the critical p-value for that inferential statistic. And we make our conclusion, where we're either going to reject or fail to reject the null hypothesis. And then we interpret it from there. Let's start with continuous outcome data. We're going to, again, split it between continuous and categorical. So our outcome was measured continuously. You've calculated means and standard deviations. You want to know if those means are significantly different. So this is what we're going to do. We're going to compare the means. We're going to then talk about calculating t-ratios. We're going to talk about the properties and probabilities of t-ratios, critical values, significance, ANOVAs, and correlations. So here's the data that we've been looking at. Do you kill 1 to save 5? 1 was definitely not, 5 was definitely. Were you in close proximity or were you in distant proximity? There's the data. It's a little bit different from what I showed you earlier in the week or last week because I deleted the people who didn't answer the third question. So this is a different subset, but it's still, this is everyone who answered every question. So we can start just by comparing those means graphically. The answer is, I don't have enough information to decide. Are those means the same? Oh, you don't have enough information to decide. You're going to need to know the standard deviation and do a comparison there. Looking at it graphically, don't necessarily be sucked in because this is the same data. So you need to always keep in mind the scale at which you are being presented this data. And don't just go look and go, oh, wow, that's a really big difference. You still need to say, I don't have enough information to decide. I'm going to need to know the standard deviations. I'm going to need to compare those means, taking into account the variation. So this one is way zoomed in and is overestimating the difference. This one seems to be on a pretty good scale. So this is what those descriptive statistics actually describe. There they are, and I think we looked at that just a minute ago, and we said, yeah, that's looking like we're predicting that they're going to be different. But we need an objective way of deciding whether the observed difference is due to chance or due to a real difference. Up till now, I've been giving you a rule of thumb, if it's more than 3 points, if it's more than this. But we need an objective way to decide. We're going to calculate what is called a t-test. And the t-test, we're going to take the difference between the group means. We're going to take the mean of group 1 and subtract the mean of group 2. Calculate the difference. And we're going to divide that by kind of the average variability within each of the groups. So if the means are actually, so if the null hypothesis is true, the null hypothesis is true, there is no difference in the world, then the mean of group 1 is going to equal the mean of group 2. What's going to be the difference between those two numbers when you take mean of group 1 minus the mean of group 2? 0. And you take 0 and you divide it by the variability. What you're going to get? 0. Because 0 divided by any number is 0. And so that will result in a t-ratio that will be very close to 0. Is that going to make us think that there's a real difference, or is that going to make us think that there's no difference? No difference. How about if the difference, let's say there's 3 points difference between the groups, but also on average there's about 3 points variability within each group. 3 divided by 3 is 1. And this is so clever. What if there was a 300-point difference between the two groups, but the average variability within each group was 300 points? 300 divided by 300 is 1. So by making it a ratio and dividing the difference of the means by that average standard deviation, we put it all on that same scale. So any number divided by itself is 1. And so therefore, if our t ratio is close to 1, you've probably not found a significant difference. Okay, take a deep breath. Take a deep breath, take a deep breath. Okay? You're not going to need to hand calculate this. No one's ever going to make you hand calculate this. But let's see if we can figure it out. The top, mean of group 1 minus the mean of group 2. Cool, you guys had that, right? The change in the means, yes, the difference in the means. So, but you guys, we're halfway there. You guys knew that that was going to be the top. And then the denominator, you wanted it to be the average standard deviation. So we've got the sum of squares from the first group plus the sum of squares from the second group. Remember that was partway along to calculating the standard deviation, divided by the group size. They've averaged it. They've averaged it, and then they've got like a little extra ding if you've got a small sample size, and then the square root because that's still squared. All right. We will look at more at that on Tuesday. Have a good weekend.